den vil være indvalget. Som jeg forstår det, er Azure ud fra, at du fjerner de to. Hvorfor noget som 5 til siden, du kommer med noget
Okay, welcome everyone. So today we have the first day of presentations. So I think we'll run for the next two hours, maybe a little bit more if we need more time. I think I haven't given you so much information. That's because I trust you are very mature people who know how to run these things. But I talk about that it's good maybe to set now time, something like 5 to 7 minutes per person for presentation. And we'll try to time it and be quite strict about stopping you if you go too much over time. A lot of you guys have written me and said we prefer to do it this day, and I have not really kind of done a lot of statistics. So maybe if you can put your fingers up to say how many wants to present today. Oh, that's 1, 2, 3.
That's one per group.
One per group?
One per group.
Yeah. Oh yeah, one per group. No, yeah, no, everyone, because then we can count roughly how much. Okay, that's more than half. Anyone of you who raised a hand that can wait until tomorrow?
Different groups we can at least.
So we just prepared. We are going to talk everybody like a little bit, and we don't talk 7 minutes and 7 minutes.
Okay, so you're optimistic you can do it faster. That's what you said.
Yeah.
Okay. So Tobias, you had a question?
Yeah, I was just wondering if the 5 minutes is including questions, or if they
no, that's like excluding questions.
Okay.
Yeah. So we also have some time for. Yes. Okay. Yes. Okay. So we're almost ready to start. Anyone who don't want to be live streamed, who has maybe some confidential information, cannot be live streamed. Okay. Good. So I can only kind of record one side of the room. Do you prefer here or over here? Any preferences?
I think it's better there, otherwise you have the light from the door.
Okay, we can actually, yeah, you're right. Okay, so we'll do it on this side, so remember that. So, who wants to go first?
We can start, but we need the screen for...
Yes, I'll set that up. Okay, yeah, so you are up. Jeg har sat den på det.
Ja, så kører den.
One of these things.
Yeah.
Okay, der er meget run på. Ja, okay, ja, det passer nok meget godt.
Nice.
Oh.
Oh, it's enormous. Okay, shall we begin?
Could you take this down?
Yeah. Okay, so welcome to our presentation. I'm Inon, Mass, and Niklas, and we'll show our analysis of the US birth dataset. A reminder about the dataset itself. It's simply the number of births per day all across the US for each day from the first day of 2000 to the last day of 2014. And last time when we presented, we saw that there are two ways to look at the data. One is a proper time series, advancing over time, that's on the right side. The other is to notice that each day has a peculiar distribution such that weekends are distributed differently than midweek, Saturday and Sunday, and the other days are distributed kind of similarly except for maybe Monday, which is in between. And our goal is to predict each day the number of births in 2014 given the previous years. So the methodology is that we'll try different models. Each time we'll train the model on like 13 years and then use it to predict the next 7 days in sliding windows. We will assess the quality of the prediction through 2 measurements, the rooted mean squared error, which simply means take all the errors, square them, sum them up, divide by the number of errors, take out the root. And for STAN models, we can also do the log likelihood from the posterior distribution. Closer to 0 is better for both measures. And our STAN models will use priors for the variables based on measurements from year 2000. All of them have one chain, which does 500 iterations, and we check convergence, as we did in the course, our hats and other measurements. So this is the introduction. Now we'll go to day of week models, followed by time series models.
Yeah. So we have tested various kinds of model. So first of all, the very, very basic model, where we just take day of week historical averages, meaning that we take one model for all Mondays. It's not even really a model. You just calculate what is the average number of births on Mondays, and then you say this is our prediction. This, of course, also means that we will not be able to calculate the likelihood in this case because we have a point estimate and we have no distribution across this. This is used as baseline for the RMSE, as you can see in this case, and it's actually quite, as you can see from the graphs, it's actually, at least at weekends, it actually performs quite well. It seems that just having this stable prediction is not that bad. It does seem, however, for weekdays, it doesn't really seem to be sufficient. Then we have a similar model, but that's still different. So this time we also allow each prediction to have some variance in this case. So we estimate the mean and the standard deviation for each day. And this is, as Inon said, based on priors. That is based on year 2000. So we give it the mean from 2000, and then we have to, so for the mu, we have a standard deviation, that is the true standard deviation, and then we multiply by 4 to have it give some more details, so that was not too restrictive. And also for the sigma, we used the sigma, and then for the standard deviation, we used half of sigma. And then come up with this model, so now we're able to also have average log likelihood in this case. Which is minus 56.4, which is what we can use so far. And RMC around 900.
Which is a little worse than the historical.
Because it's based on the actual predictions, so we take actual prediction, then we take the average across all the average predictions in this case. And there might be some stochastic ones. Then we tried, because we actually have, we have relatively large numbers, so the rounding error is perhaps not that much of a concern, but actually, we do have discrete values. We have integer values. So it might be reasonable to think of some kind of discrete model to use. And for this, we tried the Ragel-Poisson model in this case. A Poisson model is a straightforward, quite easy model to assume in this case. And then we have this hierarchical structure where we have, on top of each weekday, we have one distribution for the weekend data and one distribution for the working day data. And these give the input for the other ones in this case. And again, we use the word 2000 as the input for our priors. And we can see that on average, if we just use the average, but if we don't take the variation into account, only the point estimates, we see that it actually performs quite well. The RMSE is lower than in the other case. But we can also see that the log likelihood is much, much, much worse, which is not very surprising, since the Poisson distribution has this property that its mean is equal to its variance. So it's not flexible at all with the variance. To account for this, we have used also the negative binomial model, In this case, you can account for over-dispersion, which we have in this case. And in this case, we couldn't. We tried the hierarchical model with the weekend and working days, but it had some difficulties converging. In this case, why we grouped it all into one for the phi. And we used this notation of the negative binomial, which in Stan is neg binomial 2, where you have the average value, and then you have a value corresponding to the variance being the mean plus the squared mean divided by this number. So this is what the phi means. And this is quite difficult to find out which distribution it comes from. And when we see it across weekdays, there is no clear pattern between the weekdays and the weekend days. So that was from one model. We can see we have RMSE, which is very similar to what we had before with cosine. And we have much better average log likelihood in this case. So this actually is quite good, I would say. This is, for what we have tried these Stan models, this is what performs better.
Okay, so the other approach we were going to take on this was a classical time series models. In our last presentation, we thought to implement the ARIMA model in Stan. So we did some analysis of autocorrelations and found that at least lags 1 up to 7 is very important, and that aligns with the models that we saw earlier. That is there's a weekly recurrent trend. So we actually we haven't been able to implement the integration part of the ARIMA. So right now it's just an ARMA model, and we have had quite some trouble getting it to converge on the data. We are a bit uncertain why. It actually turns out that if we remove the constant term that is normally part of the constant term that's normally part of the ARMA model, it actually converged, but the prediction is a bit worse than the historical average. So we still think we need the term.
The computer still displays, but
in and out.
maybe something in the console.
Okay, this is testing your skills.
Yeah, I can continue. So in the slide so we had an autocorrelation of 7 lags, and we're just doing a moving average of 1 lag. To test sanity check if this was reasonable based, we also run another implementation from the stats model, ARMA, and it actually gave the best results until now. We get an error of around 800, RMSE around 800. So it kind of gives us an idea that the order of the ARMA model is maybe not the best, but at least it should be able to perform. So we think that we just need to dig deeper in understanding why the Stan model is not converging.
Can we pause for 1 minute to fix this? Because we have like 3 more slides.
Yeah, maybe we can...
You try to plug another computer?
Yeah. Or maybe try to take the other issue.
That's a good idea.
Yeah, and the funny thing is that the stats models, armor model, fits quite nicely with the constant term. So we also got an idea what the constant term should have been in the stand model, but we never go near that in the fits.
Yeah, like the stand doesn't want a zero intercept, just a dependency on previous legs.
Yeah. The last thing we did with the time series analysis was using Profit. So Profit is a software library from Facebook that uses stand underneath. It has currently, as I understand, 2 models: a linear road model and a logistic road model. But what it makes it nice for this problem is it has actually a very good seasonal determining mechanisms. So it will look for yearly, weekly, and daily recurrent patterns in the data. For us, we don't use daily because we only have 1 measurement a day. But it will find the yearly components and the weekly components. So the weekly corresponds to what we did with the separate and hierarchical stand models. But if we want to do better predictions, we really need to take into the yearly components also, because it's quite strong.
Yeah, so to summarize, if we put all RBCs, because not all models yield log likelihood, then unfortunately Profit wins by a long shot. And the best stand model that we made was the hierarchical negative binomial, which performs as well as the historical average, but also yields log likelihood. And we see that in general, trying to model as day of week, not the best. Trying to model as time series works better for time series data. What you see now is the end result of quite a lot of trial and error, non-convergence, convergence, try again. And as Nicholas said, we think that if we account for also yearly seasonality, the RMSE will improve. And that is it for now.
For the report, I recommend we telling more about this Profit model you picked it because it was clearly a sensible choice when we kind of getting the yearly pattern and so on. So you guys could write a little bit more about that.
Yeah.
And it was great that you could continue talking even if you had problems. That's good. You should remember others also that if you are even in some conference, that if you know that there's a time limit, it's better to continue even if there are problems.
Even if there's an earthquake outside. You never know when you get a chance to speak in front of the audience again.
But in a way that it's good to be prepared that what you can say in that case that you can't show any figures, that you should still be able to tell something. I think you managed quite well.
I have one comment/question. Using your data from 2000 as your prior, what kind of assumption is inherent in that?
The world doesn't change.
Exactly.
Yeah.
There is substationarity assumption.
Yeah. And then it's, of course, you do the worst you can because you take the first year to predict the last year.
Yeah, but you've got to choose something for the priors.
Yes, sure.
For the time series data, we could have also maybe detrended, and then we know that the price should be zero mean, etc. But for the day of week models, not so sure.
I have one more question. You start out by fitting a normal model, and then you go to fitting a Poisson variant of Poisson. Are the likelihoods you get out of that directly comparable?
I would assume so, since it's a joint distribution. You have the probability of each of these.
Yeah. But
so they are not because.
Oh, he knew the answer.
Because with the normal distribution, it's continuous, it's densities. With Poisson, it's discrete, so it's probabilities. you can't compare densities and probabilities. That's
You have to at least do some kind of correction factor.
and so if you would like to compare, then you would need to either discretize the normal distribution, and that's actually what you should you would need to discretize. So you would need to compute intervals and what's the probability in certain interval, and then you would get also probabilities from the normal model, and then you could compare to probabilities from Poisson model.
That could explain the horrible log likelihood we got from Poisson.
Yeah.
But you then in the negative binomial you got a number that was quite comparable to and probably
Unfortunately. Okay.
And it's good to also remember, even if you have two continuous, so in a way that you could also have modeled logarithm of birds, and then in that case, if you do nonlinear transformation or even linear transformation, you need to take the Jacobian into account also. So comparing continuous distributions are always more difficult in a way that you need to be certain that the normal for birds or normal for log birds, they are in different space, and then you need to take into account transformation.
Thank you.
I think you also do.
Yeah.
Easy to compare two models having friends. And also it's also, it can get also complain if you try to continue.
Okay, can we start?
Yes, sure.
Perfect. I'm Benjamin, this is Dina and Luisa, and we're working with data on medicines given to patients that have had a liver transplant. And I'll start out by saying a little bit about the data, and then these two sort of join in and so. So the aim is that we would like to. The point is that if you have a liver transplant, you get a drug called cyclosporine, or you might get that, which it has a very narrow therapeutic interval. So if you get too little, it doesn't work. If you get too much, it's toxic. So the point is that since the interval is so narrow, you would like to have a good idea of the interval before you actually start treating the patient. And to do that, it would be nice to have another thing that could sort of be a proxy indicator, and that could be something called mesolam. So the idea is to try and get a model that it could actually predict the interval, like the plasma concentration in the blood, based on something else than the actual drug that we're using. That's how the ultimate aim. So basically we have a bunch of patients that has been given, they're in a steady state, so they've been treated for several years with this cyclosporine. Then one day they're given the normal dose, and we follow them with taking blood samples at a certain sort of a certain time stamp that are not the same for all patients. And we don't have the same number of observations for all patients. Here is the data, there's the patient indicator, there's the dose in milligrams they're getting. For example, patient 2 is getting 100 milligrams twice a day, so a total daily dose of 200. The timestamp here is minutes after administration, and the concentration is it's a concentration of this drug, cyclosporine, in the blood. Just a little breakdown. We have 6 patients that have 25 milligrams, 4 patients with 50, and so on and so forth.
Yeah, so we plotted the data just to see how it looks like, and this is only to show you how different the people actually are. So 1, 2, 3, 4, we just divided it out so that it's easier to see the different lines and colors, because otherwise they'll be on top of each other. So we have the colors here are the different doses that they were given. In this example, 6 patients who got 25 milligrams, and they're ready here, and so on. And you can see that they react very differently on the medicine, and that is kind of why we do this project, to try and see if we can predict beforehand what kind of patient do we have, so how many milligrams do they need in order for the medicine to work for them. And what we work with is, or what this is called is pharmacokinetics, and we work with these ODEs. Here is just an example. It's not our data, but it's to show you so you can understand what happens in this two-compartment model which we have here. So we have 3 spikes here on the blood, and that's every time. So this is just one person, and every time this person gets an injection with the medicine, the dose or the concentration goes up, and then it goes down and goes up, and so this person had the injection 3 times. And the reason why the plot looks like this is because of this two-compartment model system. So first you get the medicine into your gut, and then it goes into what we call the central compartment, which is the blood, and then we have the peripheral compartment, which is the rest of the body, so it diffuses out, and this compartment is big and can be many things in the body. And that's what happens when the first peak, when it goes down. So it looks like the dose is low in your body now, but that's because it goes from the central over to the peripheral compartment. And then this long span here where it slowly goes up and goes to some kind of steady, that's when the medicine goes from the central compartment and leaves the body. While that happens, the medicine that is still in the peripheral compartment will slowly diffuse into the central compartment again, and the concentration will rise, and that is what happens in the body, and also why it's a bit complex to look at this system.
Yeah. So we can describe the pharmacokinetic parameters by means of ordinary differential equations. Actually all the equations can be described just from the rate constants, which would be like the Ka, Ke, K2 and K3, and concentrations, but because we used Torsten, and they estimated other parameters, like the parameters normally used, like clearance and intercompartment clearance and central volume. We somehow used their equations instead, but it's the same because, for example, clearance is just a rate constant times the volume. So in this way, we can actually describe them with just rate constants and concentrations. But we chose to use their equations and estimate their parameters.
And Torsten is built on top of STAN and developed for people working with this kind of data.
And maybe I should just explain clearance. It's a term for the amount of blood that is cleared totally from the drug within a given time unit. Normally it would be liters per hour. So 0.5 liter is cleared per hour for the drug. The clearance is 0.5. And the intercompartment clearance is similar to the clearance, just that it is between the central and peripheral compartment. So some certain amount is totally cleared from the drug, like in the peripheral compartment to the central compartment, and vice versa. Then we have the central volume and peripheral volume, and the Ka, which would be the absorption rate constant from the blood to the central compartment.
Yeah, so just to make it simple, we would like to predict this, and we do that by modeling all these parameters.
It's just a very quick step there. This Torsten thing is built on top of STAN, and they use the data ultimately use the normal sort of log normal likelihood. So it's you estimate the concentration and take the log of that and put into normal likelihood with the sigma standard deviation. So that's sort of the likelihood function behind it.
And then we have the 3 models also from assignment 6 and 7. The separate model pooled model and a hierarchical model. And for the separate model, we have just used one patient. We've done it for all the patients, but I won't show you that because we have like 35 patients, I guess. But we have 5 measurements for this patient. The time is in minutes, and then the concentration, I guess it's millimole per liter, I guess, and it's patient number 12. So we have all our parameters here. We've used 4 chains with 3,000 iterations and 1,500 for warm-up. And we can see the 5 parameters down here. And the R hat is fine, it's 1, which we can also, it's the same on the trace plots where you can see that the chains have a good convergence, I think, for all of them. Then the marginal distributions for all of our parameters. And I think I forgot to show you the priors. They are here. And we can see that if we compare, just for example, the clearance here in the prior to the actually marginal distribution, we can see that that the data has had some influence on the result, and it's the same for the rest of them. So
yeah,
x-axis is locked transform.
Yeah.
And these priors are just what Thorsten have chosen.
Yeah, it's not our priors. I think we will try to use our own, but for now we just use theirs. So we have the predictive plot for this one patient. So of course it's well, quite difficult to predict anything from these plots.
Yeah. And now I'll just go through really fast. So we also did the pooled model, and here we divided them according to the dose that they were given. So this example I show here is the people that got 100 milligrams, and so we have 8 patients. And we see the same thing again. We use 4 chains and 3,000 iterations with 50% warm-up, and it converges nicely. And we can see, if we take clearance as the example again, we can see that now the data has had even more effect on the results. So it's not just the prior that decides the distribution. But it looks fine, and all the 4 chains agree. Yeah, and then we have the predictive plot here, and it looks a bit better, but we still have the 90% interval is very large. So yeah, we're not really satisfied.
Pretty useless for the clinical setting.
Yeah, so if we compare with what we would like to see, then we don't see that at all. But it's a start.
Yes, and the final model is this sort of hierarchical model, or it's called population kinetics model, where we put all the patients together and use their sort of the individual doses and the times when they had the concentrations measured. And this is a bit more complicated as a model, and we had some more issues with it. So because this Thorsten thing is it's a sort of beta thing, and it's not super well documented how to use it, so it was a lot of trial and error as well. So what does this actually mean? So we have this omega parameter that is somehow representing intervariability between the patients. We don't know exactly sort of how and how it would be good to sort of choose well the priors, but because it seems that it's converging pretty well. There's a sort of relatively fine number of effective samples. This one has just 2,000 iterations with 1,000 warm-ups, so it's not too bad, but not brilliant either. It seems to be mixing pretty well here as well, but then if we see the marginal distributions, can we zoom up a little bit on that? It's not excellent. These omega 1, 2, 3, 4, and 5. And the sort of cut off here. So in the standard model that from the sort of the example one from Thorsten, they cut off at 2. That's why it sort of stops there. And then if you try to expand that to larger values, it doesn't converge anymore. So we need to figure out exactly what's going on with this omega thing. Yeah, but the rest of the chains for the parameters seem to actually agree pretty well. And the predictive plots are, as we would expect, actually nicer. Not excellent, but a little nicer. As you can see, there's a lot of observations where we don't have anything at time 0, which is a bit it's a problem because you need to know where you start from to have a good idea of how far you should go up and out on the x-axis in the time. So better, but not brilliant. And then just a quick look at these Pareto K values. The Pareto smooth, the importance sampling, leave one out validation. The separate case models on the left, in the middle, and the pooled on the right, and the hierarchical ones. And it's pretty clear that the pooled one is actually working pretty well. It's just one observation, one with a K value above 0.7, and one that is between 0.5 and 0.7. The rest are sort of home safe. And the hierarchical one is not working very well. So there's some tweaking to do to actually make it work so improve it. Yeah.
We have some different ideas to things we would like to change, and we need also the medical knowledge from the supervisor to understand for the priors.
And then we need to understand exactly what does this Torsten expect. For instance, the time, is it minutes, hours, the sort of concentrations, is it milligram, microgram, whatever. That makes a big difference also in the priors. Yeah. I think that's it for the presentation.
I think it was a very nice example of using notebook also as slides, and clear and nice figures. For this prediction, you have the prediction and accuracy, but the Pareto K value is not about the accuracy, it's just the how well the Pareto smoothed importance sampling leave and out works. So it's and then it can be also used as a measure of how influential each observation is. So in pooled model, since you have more data per each parameter, if you take one observation out, it doesn't change so much the posterior. But then in separate model and in hierarchical model, you have more parameters, and so when you take one observation away, the posterior changes more. And looking at these plots for individuals, you have only few observations per individual. And then that's why it is difficult with this importance sampling, leave and out, and it probably would be better than use k-fold cross-validation.
I have one question. The dosage, how do you you use that as covariate in the last model, or
In all of them.
okay?
So
That's what it predicts.
So you feed in, so it has sort of two kinds of observations. There's an event observation where you give a drop, and then observation, sort of event where you observe a concentration, this torsion thing. So we use the dose in all of them.
So that goes into
for each
in
patient.
some kind of a regression on the dosage.
Yes, it uses it. It takes that as an event, saying you get this much of this drop. Yeah.
So, but I got the impression that you kind of when you did that kind of the pooled one, there you actually kind of pooled them on the dosage.
We did.
Yeah, that's because we could also pool everybody, but they are so different depending on what dose they get.
Okay.
And they are not. So they are not. It's not a clinical trial or anything like this. This is a real people, so they already know what dose they need.
Yeah.
So they are already in steady state, and so some people need 25 and some people need 100. But
Okay, okay,
if you
so
do it with
okay.
everybody, then it's.
So I guess when you pool them on the same dosage, you don't use the dosage as a covariate because then it's the same for everyone.
Yes, because it's the doses it changes over time. So they only have the same. They are given the same doses, but then the concentration are different. So that's the.
And so it's not used as covariate. It's more like we give him this amount of drug, and that goes in the gut, and then you use these OEs to estimate how much is taken into the body, and then that's
Yeah,
modeled.
okay.
Yeah. So it's not. It's kind of a covariate, I guess.
I think let's take it offline. Maybe it's just me who misunderstood kind of the notation, so to speak. Any more questions?
I also like that when you had these two compartment models that you use the colors to solve which ones to count for too.
Yeah.
I guess we should not have made it red actually. Doesn't it might be some red
This
green?
is
but
kind of also a compartment, but it's called a two compartment.
Yeah. But with this coloring, it's now clear that
That's
you
what.
mean that the ones that have the same color are the two.
Yes.
Okay, let's thank you again.
I'm happy that you were able to, even with the still progress documentation, that you were able to get also
We got an error like this package we take like that.
You try to depreciate it what?
It was
but the great that
took
you
many
were
hours.
able to get it straight.
Yes. We're very happy with that.
Did you take the right line in?
What?
Did you check the right HTML? Yes. Yes, please go ahead.
Yeah, so our project is on describing or predicting extreme wind speeds in Denmark, which is something you might find interesting if you are a nation that produces a lot of wind power, like we do, or if you're an insurance company who wants to make sure that they have enough money to pay out when a storm hits. So what we've done is we've tried to be able to see most of the country. We've taken the 5 largest cities and found some data for the wind speeds at these 5 locations. What we find is what is called the maximum sustained wind speed, which is sort of a measure of the level of hurricane or storm. And so the data we get is when we get sort of we take data from the year the 1st of January 1995 to the 31st of December last year, and so we get this time series. In principle, we get a time series data, but we just use it as a sort of collective data. And so we have the 5 cities. The first, so we didn't put labels on it, but the first sort of peak you see is Copenhagen, and then Aarhus, and then Aalborg, and Odense, and then Esbjerg in the end. And as you can see, for Aarhus, which is number 2, it has some more extreme wind speeds. So it seems that Aarhus is very windy compared to the other cities in Denmark, apparently. And so when we want to model this, and we want to model the extreme values, which means we look at the tail of the distributions. So here you see sort of a combined histogram of the wind speeds overall, and then we have to choose some cutoff value that we will get into how we choose later. But then everything above the cutoff value is what we use as sort of the tail for that we want to fit our model to.
Okay, great. So now I'm talking about what we actually did. So what we modeled is what Aslak said, this tail, what you see behind this cutoff value. And for that we used a generalized Pareto distribution. And what a generalized Pareto distribution is, it tries to fit the tail of a distribution that contains a lot of those extreme values. And just to give an intuition, because we're going to talk a lot about those shape parameters, you have a scale parameter sigma, and you have a shape parameter xi. And those affect the Pareto distribution in a way For example, you can see that if sigma goes down, you actually have a tail that decreases faster. And on the other hand, if you have Xi values, those are the curves, the red curve and the brown curve. If Xi increases, you get a longer tail in the end. That means if you sample from this distribution, you get more extreme values in the end. So that's how a generalized Pareto distribution tries to fit such a tail. But it also shows it's a bit delicate on how you choose Xi and how you choose those shape parameters. And in the end, that also affects how you can actually choose a prior. That makes it quite difficult. So how to choose a cutoff estimate in literature is discussed. If you look at this generalized Pareto distribution, it's again a delicate issue, like where do you actually place, where do you want to model your tail? So how do you want to model your data? What we did is we show on the right-hand side a quantile plot of all the data. If you would fit it to a normal distribution, you can clearly see it doesn't fit. On the left-hand side, it's the tail data. If we cut at 30 kilometers per hour the wind speed, and we fit it to a generalized Pareto distribution, you can see it's sort of what you would expect. And that's what makes us confident that 30 is, for now, a good guess, but we'll also discuss it in the end and talk about it later.
So now we have the only concern with the tail data. We're going to model this with the Pareto, and we're going to do first a pooled model that's treating all cities as one group, so that's just wind speeds in Denmark, you can say. Then a separate model, then a hierarchical model, which we implement instead. For each model, we're doing the marginal distributions and using some test statistics. In this case, we're going to use the maximum in each sample which we draw from the posterior. So the maximum storm which is expected in this sample. And then we're going to do some model checking with our hat, k-hat, and k-exclude, and use this to select one model to make predictions. So once we have a model, we're going to look at the evolution of these Pareto shape parameters. So how these parameters, how this distribution moves as you go from years. So from 1995 to 2017. And see if it's getting more extreme and does the weather get more extreme. And also we're going to predict, using the same time scale, the probability of what we call a storm, which will be 70 kilometers an hour sustained wind speeds between 2018 and 2040. So we start with the pooled model. We combine all the data sets and do the standard step with a non-informative prior for the scale and shape parameter. Then we find some, we draw samples from these posterior k and psi and sigma. We find they are centered the case at the, or size at the at negative values close to minus 0.06, and the sigma is close to 8. These nice histograms. And if we plot actually the corresponding histogram of both parameters for the joint distribution, we show some correlation between these two parameters in the Pareto distribution. So we can also do these other things I mentioned before. So the first thing is this test statistic. So for each repeated sample by rep, we plot the maximum and make a histogram of this. So the red line is the maximum of our data set, tail data, and that's close to 80. And we see that we're getting some quite more extreme values, that the maximum data is centered in this distribution, close to, but we're also predicting in some samples, some cases, we're predicting over 100, which is like a hurricane, which seems extreme. And the reason we're getting such extreme results here is because, as we mentioned before, that we have this Aarhus data, which is an outlier, which are predicting quite large wind speeds. So you'll see for the 7 model, this is not the case. And also you can do like a probability plot of getting above a certain value. So in the upper right here, the probability plot, you can see that there's some probability of getting over 100 in this case. And we show also here the tail data, just the pool. So this is all data in Denmark about 30 together. And then you can make a kernel density estimate of the, so this is just plotting the histogram in a different way, so estimating the probability distribution. And we show here, if you can see it might be hard, in the large blue line we show the data in this estimate, and then around it we show in lighter colors the repeated samples. So we're showing 50 samples here, so they're quite close to the data in this case.
Okay, so the same now for the separate model, and Johannes walked you through all the plots, so I'm just gonna show real quick what we get. Again, you get the posterior draws that are correlated and around values that are now matching each of the cities, and they're quite different. And we see that basically one city, and this is ours, is actually a bit out of all those estimates. But still, the shape and of sigma and k is of course similar, considering our model. What we get now for the separate model, we just show a sample city. Again, it's matching quite well, so we were quite happy to see that this generalized Pareto distribution works in our case. You can see the wind speed in this case. This is SPX again, and also just one sample tail. There's just one random sample compared to the actual tail in the lower picture to the left. So that also matched quite well, as the kernel density estimate. Yes.
And then, of course, as you might have guessed, we decided also to do the hierarchical model. And here we see again very similar results. They are a little different. The chi values are centered a little lower than in the separate model, but the sigma values are quite similar in the hierarchical separate model. But it is quite a bit lower than for the pooled model. And again, we see that the posterior distribution, we see some correlation between the sigma and chi values. And again, I mean, this is very much a repetition of the separate model, because in the end they are not very different. I believe this is because we have a lot of data to plot and or to fit. But we see that it fits quite well with the fit data fits quite well with the real data, and but we see for the kernel density that the real data seems to have some discrepancy with the fitted data. You see, for example, there's a bump which is not captured, of course, by the Pareto distribution, unfortunately. But other than that, again, it looks very similar to the separate model. And so, of course, we want to know which one is the best. And so, we won't show you, but I can tell you that all the R hat values are close to 1, and so everything is converged. It's very nice. And then if you look at the Peters Lou value, for example, you see that the pool model is clearly the worst. This loses to all the others, but the separate and hierarchical model are very, very close. And you can actually, I mean, if you do some fiddling around with the priors, for example, you could make hierarchical win by just a small margin. So they're very close. And if you look at the effective number of parameters, they all seem to follow quite well. So, for example, for the pool, you get almost 2, which fits well with the 2 value parameters we have. And for the separate hierarchical, we have 10 parameters roughly. And all the k hat are below 0.7. So everything converges and is nice. And so the question is now, because now we've seen we have all this there, we've had some storms now. Will we have a storm in the future? And so here we look at all the cities, and we chose this cutoff value of this above 70 kilometers per hour. And you see that if you use the separate and more or less similar with the hierarchical, you see that in Copenhagen there's almost no chance of a storm, which is kind of weird because we have actually had quite a few of these storms in the past few years, like Gorm and Bodil, and these nice storms have actually performed better, shown more than 70. So it seems that there could be some indication that there are some extreme values that we cannot catch with the model. Whereas Aarhus, of course, has 100% probability for a storm in the next 23 years. And then for the rest of the city, there's a non-zero probability, but it's not very high.
Okay, for the sake of time, I'm going to make this a bit shorter. So we also looked at this parameter evolution in a way. We have 20 years of data. So let's say now we cut it into 4-year pieces. So we get 5 time intervals. and we look at, we fit the model for each interval and see how the shape parameter and how they actually evolve over the years. So this might seem a bit all over, and it's really just an estimate to show what we wanted to see if it works. What we get out of this is basically a trend that our xi value goes up and the sigma value goes down. And what does that mean for actually this distribution? We want to show it the example of Esbjerg. So again, you can see, you look at those different time intervals. The error bars, those are actually the 95% credibility intervals. So how certain are we that those values are going to happen? We say that the values are going up and sigma is going down. That means for the Pareto distribution, we just show from the first time interval and the last time interval how this distribution looks. So how do we draw the samples? And a way to attempt to explain what happens is basically that there are lower wind speeds in the tail nowadays due to the wind power capacity that have been ramped up in Denmark. That's an idea. Or the other explanation, more extreme wind speeds due to extreme weather that cause the Pareto distribution to change. And that just matches quite well with saying that this Pareto parameters actually change if you look at them over the years. Yes?
So there is some arbitrariness in this model in choosing the cutoff value. So what we did so far, what we found in some papers, is that you do this fit to a normal, and then you check when the data goes away from this normal fit, the red line here. So this is what we've defined as the tail. So the middle green line here is 30, the cutoff we used so far. So now we'd like to check, and we want to show this over here. So now we'd like to check whether decreasing this by 5 or increasing it by 5, so taking 25 or 35 as cutoff, does this impact the results in a major way? And if the fit is good to agree to it, really should. So we do simply rerun the analysis using these values. What we get is that when we compare models again, have we only compared the hierarchical and the separate model, that they perform the best. That the number of effective parameters that you take as a function of the cutoff in the top, you get that it's quite stable as you increase the cutoff from 25 to 35. And the same is true almost for the prediction of a storm in Esbjerg. So it starts out at about 3% in both models and goes down to 1 if you go to the extreme end of the tail. But the results are quite close in all cases. So as you might be able to see, the best model depends a little bit on the cutoff because they're so close. And the last plot down here with the black dots is simply the normalized blue difference. So as you might be able to tell, they are very close. The difference is 0.02% at most. And by switching the cutoff, you can switch from the separate model being the best at the start to the hierarchical model being the best at the end. But it's a very small difference.
Okay, so final remarks on what we find out. So we were pretty happy to find a separate model that, at least for the test statistics, showed good results. We see that this xc value is always below 0, so this is the shape parameter of the Pareto distribution. There's some issue about the Pareto distribution because the way it's defined, it's only in a certain range where you actually get probability. So if you exceed a certain value, the probability is basically 0 if you have this shape parameter lower than 0. And what we just done down here is we show a data set for values of a negative xi value and the sigma of around 6. And we do the same draws for a fixed sigma value, but a k value to see of 0.05. And what you can see, you suddenly start to predict really extreme wind speeds. So as you go into the future, it might not be the best model to use this generalized Pareto distribution for Denmark. As we see, it's gonna predict extreme wind speeds, and it's a bit delicate in the way of how you use this parameter. Because if you go close to 0, that's really something that we figured out is a bit difficult to say. But as a final remark, it could be interesting, look at different locations, use the same approach, and maybe go to the Gulf of Mexico, where you actually have tropical storms or whatever. And that just as a final remark, and that's the end of our presentation. Thank you.
Could you go back to your prediction slide? Yes, that one. Maybe I misunderstood your model, but wouldn't you expect that the hierarchical model, that there the values would be closer to some mean and not further away? Because I know it's just by margin, but here actually the separate model seems like Copenhagen is a bit higher, Aarhus is a bit lower, and the reverse is true for the hierarchical model. Wouldn't you expect it to be the other way around?
But then also, the hierarchical model, if the posterior is more narrow,
yeah,
then that would make also then probabilities for the future more extreme. Whether in a separate model there's more uncertainty with other parameter values.
That makes sense. But then could you incorporate somehow, because Aarhus is not that far from Copenhagen, and in the hierarchical framework you would like, so the wind speed in Aarhus, you would like it to be somewhat influenced by the wind speed in Copenhagen. What was the mean there? Could you do that? What would you do?
And then, so how many years data you had?
20 years.
22
years.
Yeah. If it's 20 years, in some figure you had also some bump.
Yeah.
So is it just one big storm, even that can make?
It seems to be more
that
than
bump?
just one. Yeah.
More than one storm?
Yeah, it's around 42 you see this bump.
So of course 20 years is not that much for this kind of events. These extreme value analysis is really difficult because there are only rare events. It was very good of your plots on comparing the posterior predictive checking, that whether these results are sensible. It's an interesting question is that if you would know that in a way that what would be the maximum sustainable wind speed anywhere ever in the world measured, that how you would include that kind of prior information, because now you have only parameters for sigma and xi, but then how you would include information about what are the most extreme values.
Yeah.
One way would be then of course constraining sigma and xi so that you would, because you have the property that if xi is below 0, then you have certain upper limit.
Yes.
So you could have that kind of joint prior for xi and sigma saying that you have some, even if it's not a smooth prior upper limit there. Now you had can you show the joint posterior
For hierarchy.
here?
Yes.
So you had now some draws with k larger than 0.
Yes.
And then you could have a prior then which would say that you assume that it has to be below 0, and then jointly for k and sigma that what would be the kind of maximum you would
I think once we use gamma prior for the k value, so it's gonna be larger than 0, and then it's really extreme.
Yeah.
So yes.
And then of course there are other extreme value distributions with more parameters, so that would bring flexibility. Then when you looked at the change in k during years, now if you give the joint distribution, if you go back to that joint, so in a way now that because of this dependency between k and sigma, it means that the marginals are wider, and when you make this plot in time, you could have plotted just the change. I assume you plotted now the marginals.
Yeah. So what do you mean just plot the?
If you would make the kind of time series model
Yeah.
for that, you would get draw.
Now you have the problem that if you look at just one time point, and then you have, for that one point, you have k and sigma, and they have this distribution. Now if you model at different time points, k, and then you have these different plots, but if you have a time series model, you would have, these k's could be something like this. And now you have plotted, I assume, just marginal from all the time points, or did you even make it independently?
Cities.
Or these time points?
Yeah. Yes.
But then if you, instead of making them independent different time points, you could make even just have a linear model for k, and then instead of looking at the marginal like this, you would look at the difference from the first time point, and then you would have less variation here, and then you would see more accurately that is there change in k in time. Did you get it?
Okay, so for the linear model on this.
Yeah, so you could have a k is then parameter alpha times g plus maybe beta plus.
Yeah.
And then when you look at these k values, you would then specifically look at the distribution of betas, and you might have a lot of uncertainty on alpha because of the dependency with sigma.
I have one quick question. Do you think there's an error in the data for Aarhus?
Yes, we also discussed this. Yeah. I don't think any of us. I don't go to Aarhus so often. I don't know.
I don't think it should be more windy than Esbjerg.
Okay, so it's not like, I mean, but that's okay. Maybe I should phrase my question a different way. Do you think it's due to a general that it's more windy in Aarhus, or do you think it's due to a few outliers or extreme wind?
I would say it seems to be because it's more windy in general.
Yes.
Right? If you examine the river at the left side and plot, I mean, as more extreme values, you can also see that sort of
Okay, so that's
with the data points that we have, where so the cutoff starts is quite a bit wider than the rest.
So this top. Okay, we should explain it. Okay, so you kind of
sorry.
order the after cities there. Okay.
Yeah.
I feel like if I should make a educated guess on the most windy city of those you have, I would say Esbjerg, because it's just out in.
We would say the same.
It could also be that the observations.
Yes, there can be data issues. So last year there was one big storm in Finland, and the Meteorological Institute told that they don't know what was the strongest winds, because the automated system decided that there's an error in the system. It's reporting invalid values. And so it didn't store that strongest measurement. It just discarded it.
Okay, thank you guys. So I suggest we take a short 5-minute break, and then we start again 14 minutes past on that watch. That's funny.
How well these different instruments work.
the Bayesian wind speed would take
somewhere in the presentation report, they said this is state of the art, and I don't think it said that about the confidence band. I think it's nice because the frequentist model is like one of the best frequentist approaches. And then you say like here's a Bayesian equivalent that's kind of better. And then constant sampling is what is like of confidence bounds. You kind of have a randomly multiplied better 1 over like 1 minus 1 over 2 times some constant which is sort of arbitrary. And it's kind of something that you choose. Thompson sampling it's kind of automatic balance exploration and exploitation. And that's what
but this way, the code is only the same.
Oh, I don't
be more, so the peak would be less correlated.
Yeah, I think you're right. I mean, so what I can see, most of the things are only they can prove asymptotic optimality. So they reach this will vary from and I don't think that I think most of the approaches, at least all the Bayesian approaches talk about, will all reach the same optimal point in the long run, I think. The frequencies probably will hit something that's a constant worse, but not too much worse, I think. But it's not really.
While?
Yeah, I don't know.
Lower than 2 minutes.
It would be nice. And I think, I think it would be nice to be able to run K equals 200 or more, also like more episodes, but also like 5,000 minutes. I don't know, you probably need to 10. Yeah, 10 steps. Here they've got a factor speech rate, but this one is definitely converged, I would say. This one is almost converged, this is like not even close.
When it's converged,
I would say so.
Man har fundet et eller andet, rigtig godt data på et eller andet, der er fedt, man kunne bruge. Like with 5,000. Man har lavet one star, like even every other place. Maybe the difference gets bigger.
Kind of looks like the Thompson sampling could close the gap, right? There's also quite a lot of noise in these, so it's not like the most scientific thing in the world. Yeah, I think they do.
5 seems.
2 seems to be a little. Yeah. I mean,
but it's
Okay, so let's get started again.
Okay.
Toga Maciek, please.
Yes. So I'm Toga, this is Maciek, and we are working with Bayesian reinforcement learning. And reinforcement learning, just quickly, it's goal-directed learning from interaction, where you just receive some reward as a scalar, and then you seek to optimize this. Bayesian approaches, like just very quickly, we explicitly model the probability densities, and we can incorporate domain knowledge through priors, and it's really neat that it enables hierarchical approaches.
this is useful for several things in reinforcement learning, and the thing that we're focusing on here is how to solve the exploitation dilemma in a principled way. So just quickly, what this is all about. So reinforcement learning is often measured in the where the objective is to minimize regret, and regret can just be said like, what's the difference between whatever you did and what the optimal action in that situation is. So we just have a term here where we just subtract the rewards or the cumulative rewards from the optimal policy with a star and then your policy. So we chose to work on probably the simplest environment possible, which is just multi-armed bandits. So the environment can be described as k parameter vectors theta k are sampled from some distribution, and then at each time step the agent will select one of the arms and receive a scalar reward based on the distribution of that arm. So we started with just Bernoulli bandits, so reward of 0 or 1 for k's from 2, 20, and 200, where the thetas are just sampled from a beta distribution, where we just chose some pretty arbitrary numbers of alpha equals 10 and beta equals 40, just such that the uniform prior isn't actually the true distribution, to have something interesting. Yeah, and then the reward are just sampled from these. So as far as agents, we kind of wanted to compare different agents and see how they perform under with these different values of k. So there's the two baselines are just a random agent, and then something we call frequentist upper confidence bound, which I'll describe in a little bit. Bayesian upper confidence bound, which is the Bayesian equivalent, Thompson sampling, and hierarchical Bayesian upper confidence bound. So the upper confidence bound algorithms are the basic idea is just have an optimistic estimate of the value of everything, and then you'll kind of explore each arm, and then you'll be sure that you won't miss the best arm. So in the frequentist approach, you just pick the arm that has the highest mean plus, and then we have this exploration term where you can see that just at every time step the LNT will increase, and every time that you pick the arm, the TK will decrease the term. So this will kind of make, if it's a long time since you pick this arm, you will the agent will be incentivized to pick it. And it's a sort of heuristical exploration in a lot of ways. And then the Bayesian, the Bayesian equivalent is where we, of course, we model all the distributions, and we model the posterior of the parameters, and then we pick the action that maximizes the quantile that's proportional to 1 minus 1 over t of the posterior of the parameter. And this is also a way, like, we use the quantile instead of just the mean in order to have this optimistic bias, so we'll keep exploring.
So then we implement Thompson sampling, which is in principle quite similar to the previous upper confidence bound bias, but it differs how we select the arm that we will draw samples. So we basically update posteriors for each arm, similarly as in the previous bias approach, but here we sample theta from the posterior for each arm and select the arm with the highest sampled value of theta. And this is apparently the state of the art in terms of Bayesian reinforcement learning for this problem. And we also combined a hierarchical model with UCB, Bayesian UCB. So we assume that different arm probabilities follow the same distribution, and in our case it was a beta distribution that we specified. In the separate model, there is no such assumption, so we assume that if we put some common prior on them, they will be able to quicker find the optimal arms. What we do here is basically to estimate prior based on historical samples from all arms. So we get the means from the arms. So it's like point estimates from which we estimate alpha and beta for the prior distribution before every next action. Of course, this is not fully Bayesian because there is uncertainty about this alpha and beta. So we will probably next week also consider making full Bayesian, so putting hyper prior on alpha and beta to compensate for that uncertainty. And these are results. So the first two plots for K2 and K20 are for average over 25 episodes. So we can see that Thompson sampling is best separate model out of all of these three models, out of all of these models. But if we consider hierarchical Bayesian UCB, then it outperforms the other Bayesian models, especially for bigger Ks. So for K20 we can see that it's better. It's not actually better for K2, but with two samples it's hard to estimate the prior precisely. So there's still a lot of uncertainty. And with higher K, we get more knowledge and we're better in estimating the prior. For K200, we only run just now quickly 2 episodes, so the results are quite noisy. But we can see that hierarchical prior is already much better than the rest. And what we plan to do next, so we want to repeat the experiments with more episodes and more arms. We want to implement probably a hierarchical model for the Thompson sampling and a fully Bayesian approach for the UCB model. And try other distributions than binomial for the reward. So right now the reward is either 0 or 1, so either you win or not. But the reward can be also like a continuous number, so we want to try with continuous bandits. Yeah, and we might also have a question because we were not using right now stan because it's all like analytical updates of the posterior, and we're wondering if we need to do it and if we need to do it, how we could do it, because we're running like millions of time steps, millions of actions, and running stan 1 million times seems quite expensive to compute posterior every time. Yeah. Yeah.
So no need to use stan.
So now it's our turn to ask questions. Anyone in the audience? Very nice stuff. I have one question. I mean, of course, this is kind of a very controlled problem in the universe, and I think it's a very good idea that you selected that to see these methods kind of play out. Is this relevant for more complex reinforcement learning?
So I think a lot of the benefits with more complex reinforcement learning is if you have a model, especially if you have like the transition probabilities, then you can really, like, it really lends itself better to a lot of the Bayesian stuff. So I mean, a lot of the things that are really hot within serial reinforcement learning or deep reinforcement learning, like doing stuff with images, I don't think there's an easy way to do it using the methods that we have right here. So they kind of it's quite hard in like very in more abstract environments. So like in a maze or something, like how do you actually model things in a reasonable way? It does become a lot harder. But I think in model-based and planning type applications, it does make sense.
It might also like maybe work better in stochastic environments where there's more uncertainty. So when we make an action and we're not sure about what we will get as our reward, it might be either win or loss, depending on some parameters that we don't know and that change, or it's like stochastic.
Now we learned before that Facebook is using Stan, so it could be that Facebook has a bandit model for all of us, and all of us who are on Facebook.
Is there an easy way to understand if you want to like recompute stereo like many times? Like, can you do it in a way where you don't have to compile it?
So you don't need to compile it. You can run the same model again without recompiling.
With a new data set.
Yeah.
Yeah.
And then currently it's not so easy. So because it usually does the adaptation and warm up. There are also ways how you could skip that, so that if you could reuse the same mass matrix and then make a shorter warm up, but that's a bit tricky. You can find the instructions at least in the discussion forum if you are really interested in. But then that's also in a way that it's you save maybe 40% of time, and so that's not so big issue usually.
Okay.
Thank you. Okay, who will be next?
I come from Bayesian Nordic, and we have investigated a process change to evaluate if we would actually get higher activity in our product if we did sort of an optimized process. What we also did was actually investigated on a small and a large scale production facilities, because it would be beneficial if we only need to test our new processes on a small scale facility compared to a large scale, because it's very expensive to run tests on a large scale production facility. So we would, so I have data for both the small scale and large scale, and current and change production process. And I would like to answer if the small scale facility sort of mimics the large scale facility, and I would also like to know if the current process or the change process is better than the current process. I have been working on a very limited data set, because usually it's very expensive to run these kinds of tests, and a lot of people are involved, and it takes a lot of both production facilities and also testing in laboratory, which is also quite expensive. So this is basically my data set. I have data for the change and the current process, and large scale and small scale. And what I wanted to do was, I would like to investigate if there is a different mean in each of the groups. So I have simply estimated a different means for each of the groups. And then I have evaluated the model with the efficient number, the R hat, etc., and the K Pareto values. For this first model, where I have evaluated, I get okay Pareto values. They are not all nice, so I would also like to investigate if a smaller model would give me the same kind of results. So I reduced the model a bit, estimating. Still, I was estimating a mean for each of the group, but I said that I sort of estimated a mean for the large scale and the small scale, and a mean for the current and the change process. And again, I get okay results. The Pareto K are okay, but I thought that, and I actually did a comparison between the model A and the B, and they were on similar levels, taking the standard error into account on the comparison. Then I went to the last model where I reduced the model, so I would only look at the change of the process. So I was only looking at the current and the change process and sort of ignoring the scale. And here, when I compare it to the model B, I actually got a better model, so actually a significant better model taking the standard error into account. And we can also see actually all of the K Pareto values are below 0.5. So it seems like a relatively good model, this one. Then I did a model check. So I had done the model-based data sampling. And first of all, I did a histogram just of all of the 16 data points. And you can see from this histogram, I have actually quite a large amount of numbers between 8 and 8.2. And it seems like the model repeated data are not capturing this sort of trend for this high values between 8.0 and 8.2. And just checking to the original data, the range between 8.0 and 8.2 actually have quite a lot of numbers in this range. So that is not that nicely supported by the data. The reason why I still think it's sort of okay is that I was evaluating the 2,000 samples I got from these model-based data, and I saw that in more than 350 samples, I had 6 or more data values above or in that interval which we are talking about. So I think it's considerably likely that the original data is not contradict anything that I have done in the model. So my conclusion is that it seems like the small scale, large scale actually mimics each other quite nicely, and also I can see that the mean value of the current and the change process are relatively different. And that was actually what I wanted to know from my study. I wanted to say something about the scaling, and I wanted to say something about the process. Yeah. So.
I remember you mentioned that you would like to use strong priors.
Yeah, and I forgot to say, but I actually did. I will just go to the notebook. Because I actually use strong priors. I forgot to mention that, and now I lost the connection. Why is that? I actually use strong priors. So I had a strong prior for 2 of the 4 groups. And actually that caused me quite a lot of problems because it was quite difficult to define that I have a strong prior in one group and not the other one. And that causes some problems in defining some of the stand models. For one thing. Another thing, then I actually tested the model C without any prior information. and the prior information are not providing any significant contribution to the model. If you're looking at marginals, it is better, but not on a significant kind of impact, which was relatively disappointing, I must admit. But it actually caused me quite some great problems, especially in defining the model with only the main effects. I needed to add an extra 3 extra parameters, so I would sort of capture the impact of the process and the impact of the scaling, and then calculating the means afterwards. So that was not so direct forward as the full model or the model for just one parameter. But these priors actually cost, it's quite difficult to include priors for one group when you actually wanted to. So I had a prior up here, but I wanted to evaluate the entire change process and the entire current process. Yeah. So I'm just wondering, is it expected that the priors are not contributing too much to the conclusion, or is it because they are very close to the data used that they don't improve significantly in the modeling process, or is it because I only have priors for 2 groups and not for 4 groups?
Yeah, that definitely, both, so that in a way they are close, so they are not disagreeing with data.
Yeah.
But also then, when you are looking at the differences, and then you have prior only for current large and change small.
Yes.
Then there's less information about the change.
Yeah. I was tempted because when I'm talking to the scientists with respect to the production process, they are all saying it's the same variation regardless of what we're doing. So I have actually been tempted to try to include more priors based on their, but I didn't do that for the way it is now. Yeah. And what also, I think these data points are probably causing me some problems, the ones with in the small current. These are probably the ones that are dragging my distribution to be in this a little bit skewed way, and I'm assuming a normal distribution for my data. So I don't know if that's the reason for this.
Yeah, so I was also wondering, but I mean, you have so little data, so you probably cannot see the difference between a normal distribution or anything else.
Yeah, I was wondering if a t-distribution might catch the tails a bit better, because perhaps this is sort of a tail sort of issue.
Yeah.
But then when I did the repeated data model-based data, I actually saw quite a lot of samples with the same range of numbers in that area, and then I thought, okay, then perhaps the normal distribution is capturing the data quite well.
Yeah. I think the problem with t-distribution, and Aki can correct me if I'm wrong, would be that you have nowhere close enough data to actually estimate the number of degrees of freedom. So you just have to posit 5 or something like that, and then trust that. And then when you talk with Bosch, she asks you, why did you choose 5? Say, oh yeah.
but then I could argue 3 because I have 4 in each group.
Yeah. Yeah. That you can also argue, but I don't know.
No, I don't know either. That's actually why I gave up on the t-distribution, because I had very difficulties in actually saying anything about the number of degrees of freedom.
I would say that with these few numbers, it's really difficult to learn shape of the distributions and then it's just fine use normal distribution.
Yep, and actually I did sort of some checking on it, and it seems like it is okay, and the data is reproduced by some of the samples in the model-based data. So in that sense, I think it's quite robust actually in that sense. The first model where I did all the interactions, it's not very robust, so I don't think that's the correct model to choose. But this last one, and then I actually had 8 observations in each group. Yeah, but it's not a lot of data, and yeah, and the priors didn't help too much. Which I actually hope they would, because normally we would do an experiment and then sometimes we can find additional data, but they didn't do too much. So it's probably when the priors are very different that they could use, that they would give some additional information compared to the data, or compared to the
yeah, and also if you would have for all groups, then
and for all groups,
that would reduce the uncertainty.
Yeah. Yeah. Yes.
Who's next? Nobody wants?
Did we have all?
Did we have all for today?
Great.
Great. I mean, first time ever on time. Yes. When is the final handle? When do you want to hand it? What is a good idea? What is a good suggestion? 2 weeks, is it too little or too much?
We have to go travel for 5 days.
Is it possible to just open the possibility to hand in for some time?
Yeah, I mean, one year I was too slow, and then the grading list kind of disappeared, and I had to do everything manually, which turned out to be much easier than doing the electronic, but that's another story. But so I mean, I don't want it to. I mean, I guess the deadline for handing in the grades will be, for me, will be something around June-ish. So we should. So 3 weeks, I think, something like beginning of second week of May. Is that okay?
You're gonna post that?
I'll post it. Yes, I'll post it.
Second week.
Okay. Yeah, beginning. Yeah, like yeah. Is that the 13th? Is that Monday the 13th? Yeah.
We're not doing peer grade right on the reports.
Sorry?
We're not doing peer grade on the reports right?
Peer grade.
Peer grade, okay, yes. Yes. And I can see that I have a small present for you guys, yeah?
Yeah, so all who presented will get stamp stickers. And then those who didn't have to wait for tomorrow, those.
Less early will never get one.
And of course, so that you can take a sticker to your group member if they can't be here today.
Yeah, take one, so you cannot take one.
That's difficult is getting this open.
Legal? Yes. It is less than 17 meters, and it is not locked.
This is
We could have moved that way.
I have extras if you want to take to your, if you know friends who would love to get.
Yeah, we need some.
No one. Tomorrow. I shouldn't put it on this computer, you must include it in the
So I implemented, you remember, the Microsoft